Okay, so welcome to the October 2024 First Fridays, and I think this is going to be one of a series of presentations exploring the potential of using the bridge as a tonal adjustment. So I'll turn it over to Joseph and Luca.
Thank you, Fan. It's great to be here. And this all comes out of the Cambridge meeting with Jim Woodhouse, which for me was, gosh, the most exciting and consequential acoustical meeting since the blind tests back in Paris. That was, and I really came away feeling there was a whole new direction had opened up. And it goes into the question I'm trying to get at here of a potential of an instrument. We associate an instrument's potential with its corpus, basically, and independently of the setup. And it's easy to imagine a Strad set up terribly that sounds no better than the factory instrument set up well. The only way we have, though, of testing things is to measure or play a fully finished instrument. And you can never, or I've never been able to say how much is in there. Is it just that I haven't tried a wild enough combination of setup adjustments? And I've been particularly interested in the bridge and how far we could go with that. We know that the bridge as a filter modifies the body response, but what is the body response? What are we trying to modify? And this is where I think bridge foot measurements come in. At any rate, let me get to the first slide. Yes, so anyone who didn't hear Jim's talk on the bridge model and the work we did at and after Cambridge, do see that. It was wonderful, and it's all available at Euphonics chapter 7.5, written out with his trademark crystalline clarity. So what he doesn't talk much about is the radiativity side, and that's something I've long been interested in, and mostly for the fully assembled violin. But since then, I've been getting deeper and deeper into the body of the instrument, as it were. So, how can we measure an instrument's tonal potential, and what does that even mean? Here's an optimistic assumption based on Jim's work. If you know the admittance matrix for the bridge foot locations and the associated radiativities, you know everything you need to predict sound output and playability for any possible bridge. So that, if you can do that, that's the place to measure when you're finishing an instrument. As makers, I think we want to get at the quality of the instrument as early as possible. For example, I think that's what tap tones were all about. This magic idea that if we could just tune the tap tones, we could predict the quality of the instrument later on. Of course, it didn't work. And one reason it doesn't work or doesn't make scientific sense is there isn't any model from getting from the top to even the completed instrument very well, let alone to the admittance and radiated sound and bridge activity. So we've been stuck on the outside of the instrument. What Jim has opened up with the bridge model is a mathematical way of getting from the top of the bridge to the bottom. And so we can start looking there. Now, a caveat, in order to predict sound with Jim's model, you need to describe the bridge in by a number of parameters, and that turns out to be not so easy to do. So we can say the acoustic potential, as I'm using the term, for a given bass bar and Soundpost is captured by the bridge foot data. Once we have a Soundpost model, the same would be true for an instrument without the post. And even as we speak, Jim is working on that. I can't wait to see how far he's come. So some complications. The bridge model is a model. It's not perfect. There's some limits to it. The properties of individual bridges have proven difficult to measure, surprisingly hard to get effective masses accurately. Even measuring the frequency in a clamp, there's variables, and we're experimenting with different methods. That's ongoing. Admittance measurements are well understood theoretically, but there are practical difficulties such as the accelerometer mass. Jim uses a mathematical compensation method. If you use a vibrometer, then there's problems of pointing the vibrometer at the same place the hammer is tapping. So just practical difficulties. Now, radiativity is relatively easy to measure, but the results are incomplete due to a limited number of mic positions, and they're compromised by mic distance and room acoustics and a whole set of questions. But imperfect measurements can at least point us in the right direction. So what is bridge foot radiativity? It's not a term that's commonly used. What I mean is radiativity measured at the bridge foot location on the unstrung instrument. So you tap the center of the bridge foot, a mic records the response. You do that at each bridge foot. You can do it at any number of microphone positions. In the measurements here, there is no chin rest on the instrument, either with the full radiation measurements or with the bridge foot ones. So to do it, I had to actually redesign my equipment substantially, because if you have a pendulum mounted hammer high up, it's hard to get in there with the fingerboard and a bunch of other questions. But it ended up working very well. Can you see my pointer, everyone? There's a little a photo rotation stage there, which lets you change the hammer angle. It's indexed, but you can do it to any degree you want. Underneath, there's a rotation stage that has indexed, that's indexed for 12 positions around the instrument. The hammer there's a solenoid, it's a custom-made arm, and it's a rubber band that's providing the restoring force in place of gravity. And the fact that it's not dependent on gravity means you can tilt it at angles and do all sorts of things you can't with a gravity operated with a pendulum. And then there's an XYZ stage, so you can position it. I've recently moved from sort of prosumer equipment to professional stuff. It ended up being no more expensive, really. The same impact hammer, but using a PCB microphone, and they have this wonderful new power supply which digitizes as well. So all you need is that in place of an octacapture, a bunch of cables, a bunch of power supplies. It's really beautiful. So the Obi, what are we called? The Obi Foundation fan, is that right? Something like that, Obi Acoustics Foundation?
The Violin Acoustics Foundation.
Okay. We now have 2 complete setups with rigs, and which Luca's using one of them now. We want to lend them out to people doing interesting projects who need some equipment. So people are interested in that, let me know. So this is in operation. And that's tapping vertically at the top center of the bridge for a regular radiation measurement. And then the same thing, tapping horizontally. And then for bridge foot, you have to and the nice thing about it is it's really very quick to go from one to the other and to adjust for different instruments. So we're taking as the default driving point the center of each bridge foot, but of course there's many places you could measure, and so we did study that in some detail, and it turns out to be very interesting, and Luca will give a full report. I'll get into some of that later. So terminology, B and T, I stand in for the bass and treble foot measurements. BT means a real average of all 24 measurements. And just as H and V refer to horizontal and vertical taps. So if you see H and V, it's talking about a full radiation of a fully assembled instrument, whereas BT is a bridge foot radiativity. So here is a single violin. The bass foot in black, the treble foot in red. And It's not really very surprising. There's more bass output from the bass foot. It goes down somewhat with frequency. Now, this is going all the way up to 15 kilohertz. We're not used to measuring violins that way, and because the bridge is cutting off. But without that is extraordinary. You can keep sailing up past 20 kilohertz. Basically, a violin will just keep projecting, probably supersonically. Now, so the treble is just this slope upwards, but we see kind of maybe the makings of some of the features. These only are put here to give the frequency range in which these are lying. So there does seem to be a big upper hill and a bridge hill. What's interesting is down here, if you take an average, they kind of cancel each other out. Here they add up, and then they start canceling each other out. So something goes on here, which is hopefully good for the bridge hill region. So this is averaging all of them. So this is the BT average. So it's essentially 12 mic positions for the bass foot and 12 for the treble foot, all averaged. As Jim pointed out to me, this is really this is emulating what would happen if you had a vertical motion downwards on both in phase. So it'd be like a zero mass bridge that's rigid, bouncing up and down. And to get the rocking motion, we'd subtract one from the other, and we've thanks to Chris Roberts, we've now gotten that in the Obi app. I didn't have it in time to work with it much here, but so effectively you can look at the bridge foot measurements in terms of how they are rocked or bounced upon by a bridge, which is very useful in getting your bearings on what these things mean. So the features of the radiation spectrum. Now it's interesting. We see a really large peak in this upper hill area. This is probably the individual instrument. The most sensitive point of the human ear is nominally 3.8 kilohertz. Of course, it's a broad sensitivity peak, but it does show that the violin without a bridge wants to radiate a bunch of sound there. And so to the extent we're not getting that in a finished violin, the bridge is subtracting from that. There is a kind of a bridge hill, but it's not prominent. And there's something I've always puzzled over is why the violin's so poor in radiating in kind of a key central area. I've just called it the radiation sinkhole, but just keep an eye on that as I go through different slides. So again, this is the bridge foot radiativity. Let's go to, this is a different violin. The black is the bridge foot radiativity, all 24. And the red is the, with the bridge, in this case, a bridge quite high, tuned quite high, 3.9 kilohertz and weighing 1.8 grams. Now, the most obvious thing it does is, as I mentioned before, it just cuts off radiation above the rocking frequency, which would be somewhere around here. Yeah, that's right, because 3.9 kilohertz, we see it falling off. It also should give a lift, and it does give a lift down here, you can see, but again, this doesn't seem to touch this area here. And now let's try a different bridge. This one is more conventionally tuned, 3.24 kilohertz, but the same mass. And we see this nicely lining up with this peak here. We get more in the bridge hill area, so that's one reason one might tune down if that's a more appealing sound. Again, this area is still a bit of a desert. And now a still lower bridge, 2.9 kilohertz, which is actually what people would, I think, was at one point promoted as the best or an ideal. I think Janssen and people did some papers, but I think it's at the bottom end of certainly what I would do or what a lot of makers would do. But what we see is interesting. We get a definite boost in this area, and we get significantly more in the bass too. So this is just all of them piled up together. And again, we can see the slope changes, happens earlier and earlier as we get the frequency goes down. Now, what sounds best? Take your pick. But again, nothing did much to this. Not much of this is captured. Nothing much happens here. So you're really just tweaking a rather small area. So again, if I'm thinking of what I want to think of as the tonal potential, it doesn't seem like it seems like there's more to be gotten at somehow. Now this is a different bridge with the same set of bridges, just to show the same cycle. So that's not a bad way of doing it. Let me just go through all 6 that way. Okay, so okay, the original bridge 1, down in frequency, all together. Bridge 1, different violin, down in frequency. So, and each time this went up and that went up, but we had losses up here. So this isn't very, this is nothing new, but it is interesting to see in relation to what's available, so to speak, from the violin body. So I did want to step farther, especially knowing there is a Soundpost model coming up, doing the same radiation measurement cycle at the bridge feet, but with and without post. And this is fascinating. There's just a lot of bass. That's no big surprise. We see the mode frequencies of B1 minus drops a lot, A0 drops a lot. That's not surprising. We're losing stiffness in the body. We see some interesting huge peaks here. I guess that would be C4. But what I found most interesting is that both the bridge hill and the upper hill in there are absolutely there without a bridge and without a Soundpost. It's been a long time teasing ourselves away from the notion that the bridge hill was a product of the bridge, and I'm not against calling it a bridge hill any more than I'm against calling the local subdivision Foxview Acres. It's a name that everyone knows, but no, I think the violin body with and without Soundpost has a lot to give here, and then our individual bridges are kind of curating some portion of that. So this I did at Jim's place on a violin of his. I marked out across from the outside of the bass bridge foot to the outside of the treble bridge foot in 2 millimeter increments, and then took a radiativity measurement just at 1 microphone position at each. So this isn't a comprehensive, but it shows the whole range of outputs you could get if you imagine putting the bridge in different places. So that's from that same set, just the center of each bridge foot, and it's kind of what we've seen before. More bass on the bass bridge foot, a bit more treble on the treble bridge foot. Now I've added in just a point near the center of the instrument, which I was surprised, a massive amounts of kind of bridge hill output there, and then at diminuendos again to the other side. So looking a little more closely, just 7 positions along a bridge foot. This is the bass bridge foot, but there's like huge, this is moving in 2 millimeter increments, and we see like 8 dB difference at crucial frequency levels, suggesting the placement of the bridge is very sensitive. Of course, makers know that. We're limited in a ways to how much we can use it because of, well, traditions and some things to do with the setup. But I think there's this really encourages some experimentation. Well, more on that later. This is the treble bridge foot. We see the same thing, just massive differences. I will, yeah, so the position and the spacing of the bridge feet is important. I'm going to turn it over to Luca, who he was working with for me for a month this past summer, and did a huge amount of work in detailing what goes on there. So Luca, do you want to take over? I'll stop sharing. Or should we open up for questions on things so far? If there's anything I wasn't clear about or that comes out of this, speak now, or we can do so at the end.
This is Andy. I guess I have a question that's a very naive question, but something to think about. When you pointed out that the bridge hill is there even without the bridge or the post. And I'm looking at that thinking it's defined perhaps as much, it's a territory defined by a valley on either side. Is maybe that the more relevant way of thinking about it than the fact that it's a hill? And like what's causing those valleys on either side?
Well, indeed, when you study closely at least the radiation spectrum, which is very different from the admittance spectrum, then you do see a very persistent small valley at about 2.3 to 2.5 kilohertz. It's a bit more complicated because the features vary a lot from instrument to instrument. But I'd say if you put any 5 instrument group together and do an average, you'll see those same things. You'll see a cluster of peaks, a divide, and then another cluster. Yeah, it's a good question. It's really worth trying to look at it in different ways. So I agree with trying to shift perspectives to see what's going on.
Joseph, I would suggest that we save the discussions for later, unless there's some questions having to do with clarification of your presentation.
I second that motion.
Okay.
All right.
Okay, Luca, take it away.
You're muted.
All right. Now you can hear me, right?
Yes.
Okay. All right. So this is going into maybe some relatively basic questions that we had when first thinking about these kinds of measurements, and then doing some experiments, some measurements to try to answer these questions. So Joseph already showed you the general idea. We do a radiation measurement, but not hitting at the bridge, but removing the setup and then hitting with the hammer on these veneers here on Joseph's instruments, which make it much more easy than without them. All right, okay, to the next slide. Good. All right. So Joseph kind of already touched on this and showed some measurements. In which way is this bridge foot radiation measurement dependent on the position is the first relatively easy question that we want to answer. And as he showed already, we can just move in 2 millimeter increments and get some results. And you saw already, we get results like this. And then if we want to do a lot of measurements, it gets a little bit confusing. We have, let's say, 16 measurements in one graph. It's a little bit hard to read that way. So what I decided to do to show the result a little bit more comprehensively is just use the band averages. So you can see I have the band averages activated here. And you can see for the first 4 measurements, there's already quite clear differences between the individual positions. So let's just plot these to get more of a general overview. How does the bridge foot radiation change as you move across the bridge foot, let's say. All right, so first for the base foot, we again have 7 positions in 2 millimeter steps, and we're always on the center line in vertical direction of the veneer. It's going to look something like this. So here in this left graph, you have the base foot low frequency band, so 200 to 780 hertz. And then let's say measurement 1, which is on the left edge of this veneer, is going to be this data point up here, and so on. So you get a graph like this. And for example, for this first band, you can see as you walk across the bridge foot, let's say the level in the low frequency band constantly diminishes. This would be for the next higher band. we can see here the level generally goes up. So we are looking at all the individual bands. And then another question might be, is the effect that we're observing here relatively constant over different instruments? Is it a characteristic of individual instruments or more general violin characteristic? So you're going to see multiple instruments in these graphs. So here in the right one, I have removed the labels for now. It's not really important which instruments they are. We're just interested in the question, okay, we observe a trend here. Is that relatively the same for a bunch of instruments, or is it very varied? This is the overall view for the bass foot. So you can see in the upper hand left corner, you have the lowest band, then the next band under that, and so on. And just the general overview here shows us kind of the trend as you walk across the bridge foot for all 4 of these bands. Doesn't seem to vary much over instruments. Of course, there's some individual differences, but in general, let's say, let's look at the lowest frequency band. All of the instruments just diminish as you walk across the bridge foot in radiativity. So for the bass bridge foot, it seems that at least all of Joseph's instruments that we had there for testing, of course, these were all made by Joseph, so are intrinsically kind of similar. The trends are very, very similar. Same thing for the treble foot. So again, 7 measurements across the center line of the treble foot veneer. The result looks something like this. So here we can see there are some individual differences between instruments. So you can see in the low frequency band in the upper left-hand corner, most instruments, let's say, are generally rising in amplitude in the low frequency band. But then there's 3 instruments which kind of diminish at first and then slowly rise again. So there are some individual differences between instruments. And one interpretation that you could draw from this, probably this is also quite dependent on the proximity to the soundpost and how the soundpost is located relative to these positions that we're just assuming from the bridge foot. All right. Now we have a bunch of instruments. So for each band, we can ask the question, what is the qualitative effect as you walk across the bridge foot, as I alluded to earlier? So here's for the bass foot, the overall result. So in the beginning, we saw, okay, the low frequency band in blue here, as you walk from the left side of the veneer to the right side, the level constantly diminishes for all instruments that we had. Standard deviation is quite small here, as you can see in those kind of blurred out bars. And then for the highest frequency band, for example, we can kind of see a tub shape. So it diminishes at first and then it rises again. So this would be the general trend over multiple instruments for the bass foot. And then here for the treble foot. So some slight differences. The lowest frequency band rises constantly and the upper bands, and so the highest frequency band doesn't even do that much as you compare the left to the right side, and the bridge hill band diminishes slightly. All right, one question. So this is kind of grayed out because this is one of the questions that we asked but haven't really done measurements yet to answer. And maybe it's a naive question, but if you look at a trend like this, you can easily get the idea, okay, can I pick one of these locations if I like? I'm going back to this slide. If I want to pick the very right side of this graph because I like the high amplitude in the low frequency band, can I just, let's say, just contact the instrument at that point and basically get the benefit of the radiation there? Is a naive question that you could ask that we can answer with some experiments later. So these red dots here that I've put in, we could imagine just putting like a chopstick under there or something so that the bridge just contacts the instrument at that point. Does it work like that? Probably not. Is it something to try? Yes, we can do some measurements on that in the future. That's why it's grayed out slightly. Just indicating that here again, the red bars, if you could just use that one point, let's say, you would basically get the response that is indicated by the red line here in the center, if you put a chopstick under the center of the foot. And similarly, that's something that Joseph said that I hadn't thought of. Basically the ankle of the foot might kind of define that visually, yes, it should be in the center. The ankle should be centered over the foot. But acoustically, there's no reason why we couldn't try a bridge that has the ankle doesn't really look like an ankle then anymore, far to the left side. Does that change how the instrument interacts with the bridge? Probably, but in which way? Something to test. Right. Similar for the treble foot. Okay, then also a very naive question, but one that we decided to answer. We measure at individual locations, and then if the bridge foot is attached to them, does that somehow average over these locations? Are they then connected, and then this trend is diminished? We decided to test this by simply gluing two spruce veneers to the bridge foot veneers to simulate there's a bridge foot here now which connects these points, let's say. And then repeating exactly the same measurement. So you can see I have marked out the 2 millimeter spacings in pencil here again. And then I'm just comparing the results from before to the new ones. First again for the base foot here. So 7 measurements across the base foot. Looks like this for the individual bands. So we can see there's no real change in this trend. And this bridge hill band here looks slightly different, but it's probably also measurement inaccuracies. In general, the trend itself doesn't really change at all. And then the same for the treble foot gives us the same answer. Gluing a spruce veneer to that point doesn't do anything. Our interpretation of that is that this assumption of maybe it's average because the bridge is on top of that at least doesn't work in that way. Let's see. Okay. Then the next question would be, is there a similar effect in the vertical direction? So we walked across the bridge foot location from left to right, let's say now, and now we want to do it in the vertical direction, so up, down. The same as before. I have some indication here again to make it a little bit simpler to read. So again, we will see plots like this, just with 3 instead of 7 points. And now, of course, we need to rotate that in our heads. So this point here is represented by this measurement point, and this, and this by this. So again, we're going to see trend lines like before for the average bands, for the 4 bands, just walking vertically now, and first for the base foot. So on the base foot, it looks something like this. You can see the trends, and since they're relatively small, I've also put the actual value differences, so the absolute difference between 0.1 and 0.3 in each instance. And you can see that they are all relatively small overall, so close to the measurement error of the method itself. So here we cannot really conclude any effect of walking up and down on the foot for the base foot. But for the treble foot, at least as you get closer to the right side of the foot, so let's call that closer to the Soundpost probably, you get some relatively strong effect. So above 1 dB is certainly larger than the measurement error. So we can say, yes, there's an effect in the vertical direction, and probably it's related to the Soundpost because it only shows up when we get close to the Soundpost. That would make sense to me. Right. Then similar to the question that we answered with the veneers before, if we put a bridge on there, now the 2 positions, the 2 veneers are kind of connected by the bridge. So just by connecting those 2 things, does something change? It's the question that we asked. So for that, we actually glued a bridge to the instrument, then cut off the top of the bridge and created something like this, which is kind of a beam connecting these 2 points, and repeated again the same measurement just to see is there a change in the in this effect now. So you can see I have again marked out 2 millimeter spacings here, and then I walk the hammer across this bridge, let's call it, connecting the 2 feet. Results look something like this. So again, I'm plotting for the average bands just to give us an overview. And for example, you can see as you walk closer to the Soundpost, the lowest frequency band in blue again here drops down as we might expect, I guess. The high frequency band goes up strongly in comparison to that. in like transparent colors, I've put in the trends that we observed before without gluing this thing on. So just for the naked foot location, let's say. And we can see for the base foot, the trends look quite similar, I would say. In the middle frequency bands, we could say due to gluing that piece there, the trend is a little bit weaker, but it's similar in quality. And then at the treble foot, so closer to the Soundpost, some of the trends are even reversed. So there might be some effect of linking the bridge feet to each other. Of course, this is a very experimental approach to get an idea about that question. I don't think we can completely answer it from that. It's just an indication that we can get. Or I should say, it says up here as well, of course, the absolute values that I'm showing here are not the true values. I've just pushed the bands apart so that we can see the absolute dB values are not really that important to us. We just want to compare. Okay. Last question that we could answer, since we already had a bridge glued to an instrument, which I hadn't had before, what is the effect of the strings on top of the bridge? So with this setup now, we can do a measurement similar to this. So we can have just the full setup instrument where the bridge is already also glued to the instrument, and then remove the whole setup and repeat the measurement and compare, okay, what is the effect of having strings on there, having a tailpiece attached to that. And here's the result. So in red, you can see the result with strings, and in blue without strings. And kind of, to me, it's kind of the expected result in some ways. So it's a little bit damped overall with the strings on there. Especially in the middle frequency bands, you get a lot of lower amplitudes. And especially for this peak here, which we talked about earlier as well. I don't know the name right now, but yeah, there's some clear differences that come from the strings, which are kind of the expected ones that we would want to see. All right, so that's the full report over the measurements that we did. I hope that all made sense. It's a lot of measurements that we just experimentally. So you saw kind of, we have questions and we just design an experiment to get an idea about the answer for that question. I don't think any of this is really exhaustive and we have answered everything that there's to know, but it's some indications, and certainly there's more ideas brewing, more measurements that we can do in the future to hopefully answer and then pose more questions again. All right, there's already questions, so I think we can go to the discussion phase.
All right. All right. Thank you. Thank you. Wow, that was really fascinating. If you have a question or have a comment, please use the raise hands function. It's under the reactions in the bottom of your Zoom app. And if you can't get it working, you can try messaging us, and we'll call on you. Okay, so
And Luca, maybe you could stop sharing your screen so we can see more people.
Yeah.
Whoa.
right, let's start with Colin.
Very impressive from both of you. Wonderful measurements. Very impressed. Just a very tiny point on the last one. Were the strings damped?
Yes.
Yeah. Okay, fine. That's why you didn't see any resonances. Okay. Fine. Thank you.
So
That's it.
George? So you don't have any more questions, right, Colin, for now?
No, that's
okay,
fine.
so if you could, I don't know if you lower your hands.
Yeah.
Okay, George.
Yeah, yes, thanks for the talk. Lots of interesting material and new ways of thinking about stuff that we've been looking at in the past. The thing that occurs to me is probably some of you are aware that when you look at a corpus without a soundpost, there is no bigger mode than the transverse dipole that is sometimes confined quite a lot into the lower bout and island, and sometimes it extends well into the upper bout. But that's the biggest mode that you ever see. Now, I was just, but we also noted that the bridge hill was rather high with the soundpost out, Bridge Hill region. So it would be quite interesting to look at the frequencies of those two. Well, you've got one very distinct mode for the transverse dipole, and you've got a bit more of a fuzzy kind of peak for the what do you call it, bridge hill. But we can't do that without taking both measurements. So we'd have to do the structural measurement on the violin as well as the bridge foot radiativity. So that would be, I think, potentially something interesting to look at, because perhaps those two frequencies are linked.
So if I understand you right, do a modal analysis and a bridge foot radiativity on the corpus without the Soundpost?
Yes, I'm looking at, well, I don't do bridge foot, I've never done bridge foot radiativity measurements, but I have done an awful lot of structural measurements where I look at the corpus without a Soundpost. And it's always the case that that transverse dipole is the biggest mode of all the modes of the whole system.
And what frequency is that typically at?
Oh, about 600 hertz, 580, that sort of frequency.
Interesting.
It's low relative, but it must tell you something. So when you take out the Soundpost, one of the first things you're doing is you're allowing all the anti-symmetric modes to come into play.
Yeah.
Whereas when you put in an offset Soundpost, you're suppressing a lot of those modes. Take it out, they can ring. An example is some of you may be aware of the Ganassi viol project, where they built some set of viols based on the Ganassi drawings. One of the interesting things about those instruments is they had a very, very extended treble response. So each of these things you do, adding the Soundpost and adding the bridge, is actually bringing about a treble cut. And presumably that the cost of that is considered worthwhile. But the Ganassi viols don't have much in the bass. They haven't got depth, but they do have this extended treble response.
And they don't have a Soundpost, or
Well, sorry?
they don't have a Soundpost? Why is the
no
okay.
Soundpost?
Yeah. Mhm.
There's quite a lot of other types of viols, early viols, that don't have them, but the Ganassi is just you can read about it. There's a web page about it, and you can see some information about it. Whereas there's a certain amount of information out there about other viols, but not much in the way of measurements. But certainly, Jim's friend, well, can't remember his name now. I keep forgetting things these days. Up in Scotland.
PhD student that you were talking about earlier, or which one?
No. Old geezer. Who's your friend who's measured? You did some bridge admittance measurements with on vials.
Oh, Murray Campbell. Yes.
Campbell, yes. So I mean, there's a little data set there, but there really isn't very much else. So, but in fact, those historic instruments in some ways are a treasure trove of understanding these mechanisms. So why did people move from one type of setup to another? You know, when something in its day must have been considered satisfactory and suitable for what people were using it with. Anyway, it's just a thought that there could be a link between, because obviously the stiffer, particularly the stiffer the top is in the transverse direction, the high, not only, obviously the longitudinal stiffness will also be a component.
Well, it's fascinating. I mean, for my part, bridge foot radiativity is a new measurement for me. I'd tried it over the years here and there, but I had no particular understanding of what was going on. But now that it seems an important way in, I've really been trying to learn the territory. And that's one of the reasons, Luca and I just did such a bunch of measurements, start to recognize the features. Now, the next thing obviously is to connect them in a systematic way to the sort of admittance measurements from the matrix Jim's doing, and then the other way to what's going on in the structure. So there's no lack of questions left. Jim?
You could get the frequency of that transverse dipole with a very small number of measurement points.
Yeah.
You wouldn't have to have sort of 100 measurement points on the top, like, probably 5 would do it.
Well, maybe the sort of thing we could try and plan for Oberlin this summer, these related ideas.
Yeah.
Jim?
Yeah, this is an associated comment, and just a small thing, but it's precisely to address that kind of question with the data you've already got, that it's nice to do this symmetric and anti-symmetric combination of your 2 feet. So especially for the ones without the post, that will immediately separate the symmetric and anti-symmetric modes. Just one will be much higher than the other. And I think you're probably blurring a lot of interesting stuff by averaging both of those.
I don't doubt you for a moment. And you mentioned you did a graph in euphonics that was very interesting using that. If you want to describe that.
Absolutely. I've already put one of those in with your data, but just looking at this sum and difference, and it may be that for the particular question George raised, that would identify it straight away. It's the one that looks a lot stronger in the rocking configuration and a lot weaker in the bouncing configuration. You can get that from the data you've already got just by adding and subtracting.
I can't wait to play around with it. Chris just said as of a few days ago it should be up and working. So you can put it in the equipment box. Other questions? Well, a question in my mind now is the persistence of these high frequency, hills. I want to, it's probably a dumb thing to do, but I want to go back to just the free top plate. And instead of just looking at the low modes, try and look at in the much higher frequencies. I wouldn't be surprised, given that a lot's happening in the island area is independent from the rest of it. We couldn't see these things being born right back there. Does that seem reasonable?
Yes. What's touching my brain right now is George did some modal analysis of the Bridge Island area. So we know where it starts to break up, and it's not just a simple, pivoting brick type thing. And I think you're probably seeing that in your measurements across your bridge feet, that modal type of sensitivity. So there's a couple of modes there where we're starting to see rotation around the center, and then we see kind of these X patterns with base bar and Soundpost, of course, kind of working on that. So where that Bridge Island breaks up, and the Obi Violin viola data, where we had lots of people had different configurations of that Bridge Island on the same size plate, maybe an interesting place to look, but I know those instruments have dispersed. It's not a collection we can get our hands on.
Yeah. So you think it'd be worth looking at the free plate, either freely suspended or clamped something and see what we see? I don't know.
Yeah, I would kind of like use I've always used kind of like damp sand for an edge, which gives you kind of a radiation condition. It damps out everything except for that kind of internal structure.
We'll do it on the beach.
Yeah, we'll do it on the beach. At Boeing, I was known for my cat boxes, as they call it. There's also mastic material they use for damping on drums and that sort of stuff. It's kind of like silicone little pads. They don't leave a residue. So there are different ways of taking out that gross motion and kind of getting a radiation condition. Jim's done that mathematically, where you kind of like put high damping into it and you can just see what's propagating. So
all right.
So I think an investigation of that island area is in order. And I think it's
I don't know what other makers feel, but I feel like the top is all of the potential is there. I mean, I believe that if you take a great violin, give me the top, I could make another great violin around it. Give me the back, I couldn't, or the ribs or anything else, I couldn't do a thing. So I suspect that most of my colleagues would agree with that. So the question becomes, how can we throw out the top as soon as quickly as possible if it's not working? So if there's measurements we can do that'll point to problems down the line, they would be very, very useful to have around. Colin, you've had your hand up a while.
Yeah, fine. Some time ago, it's about 7 years ago, I did a full analysis, in fact, FEA analysis of the computer and island area.
Mm-hmm.
I mean, the interesting thing is, of course, it does show from the island area alone, it has a number of resonances. And and they act as part of the filter action. So even when you just take the bridge off, you're still going to get quite a lot of structure, and it's all there in my particular paper, because I do measurements with and without the bridge, and looking at anisotropy and the effect of the soundpost and the effect of the bass bar. So there's a huge amount of data there in my paper there that needs, in fact, to be looked at to see whether or not the computations are, in fact, giving you useful information. But it certainly shows a richness in structure of peaks and troughs that you get that come from the response of the island area in particular. My personal view is that you can't actually consider the acoustics of the violin without actually considering the bridge and the island area as almost an integrated unit, because it's basically the bridge that is responsible for exciting the island area, which in turn excites the radiated modes of the instrument. So the island area has to be important. And I think everyone knows that the island area is important. But
And Colin, did you model the free plate as well as the complete body?
Yes, yeah.
And is there a paper that, or a section that addresses that?
No, I'm not that keen on free plate measurements, because as soon as you put the plates together, you're going to get completely different modes. And
Oh, that doesn't worry me. I just want to know what to expect.
What I did in my particular paper on the island area was to use the island area and the bridge in their natural state in terms of damping, but to damp strongly the rest of the top plate. And the effect of that is that you actually see what the island area plus bridge is doing, because basically it's pumping out energy, and that energy just goes out, and you're not worried about the reflections now from the edges. So it's particularly a top plate problem. And I think quite a lot of the acoustics can be separated into top plate and back plate problems. And one of the interesting things I think that we ought to take a little bit more attention about is, rather than doing these averages around the whole front and back, it would be very interesting to look at what's coming out from the front of the instrument and what's coming out from the back of the instrument. It gets very localized indeed. Modes in the front of the instrument radiate outwards in the forward direction. Modes in the back of the instrument radiate, particularly as soon as you get above a kilohertz. They're very directional indeed about front and back plate radiation. And I think, as someone else was saying, one's losing a lot of potentially interesting information by taking all these averages as you go around. But,
yeah. Oh, absolutely. But I mean, the thing is, you get a punishing amount of data, and you want to make some sense of it. So I do what I do, and then when there's a more specific question, absolutely, that's what to look at.
You'd only halve it. I mean, I'm still not against averaging it, but you could average over the top hemisphere and the bottom, as it were.
Mm-hmm.
Yeah. So you get two different results, which will actually tell you to what extent the instrument is radiating in forward direction or backward direction. And
Well-
these are important because it's the radiation that comes out forward that is actually giving you most intensity. Because the radiation coming out from the back of the instrument is going to hit you, and a lot of it's going to be either not pointing towards the audience or being being absorbed by you as a person.
Well, George Bissinger did something like that. He remember divided the thing and concluded that some violins had more to the rear than the front. I think that was just a matter of the ones which had lower treble output were going to look correspondingly bigger from the rear because, you know, instruments with a lot of treble output, a lot of it's coming from the front. But, well, I mean, it's strange. The bridge hill, if you're holding a violin, a lot of the strongest peaks go that way, not towards the audience. One assumes that the hall is averaging things out, so it's not as critical, but it's a fascinating question. George, you had your hand up for a while.
But it certainly makes a difference towards the player.
Yes, another interesting question, George.
Yes, actually, I've got a slight disagreement with Colin. If you think about an electrostatic speaker, the direction the sound comes out of it depends on which way the diaphragm's moving. So it just happens that a violin is a box, and quite often the top and the back are moving in opposite directions. But then that's not always the case. So when you say the direction that the sound is coming from the violin, that actually depends on which direction the wood is moving in, or the larger proportion of the wood. But anyway, that's not the point that I wanted to make. The point I wanted to make was that when you do a modal analysis of an island area, you can see that it's energy leaky, in that when you look at the modal circles, they're not round, and they don't fit very well with using the multi-degree of freedom systems, which is slightly surprising. So basically what that means is energy in the island area is going out into the upper bout and the lower bout and into the back and into wherever else in the structure, and it's not all coming back.
And into the air, is that part of it?
Yeah, sure, some of it's coming into the air, but the amount of proportion of energy that's going into the air is really rather small. Whether you're looking at the top or the back. So if you say, well, the bridge, we don't see a clear hill, clear sort of rocking or bouncing modes often on a bridge in situ on an instrument. Well, likewise, you know, in the island, you don't see that as clearly. It's clearer, relatively speaking, than the bridge, but it's not 100% clear because of this effect of not all the energy coming back. But I think that it does actually reinforce what Colin was saying. I think this idea of the island and the bridge working together. So between the two of them, you know, there's a lot of damping there. That's it.
Yeah, well, I mean, as a maker, I want to say not specifically how to make this bridge work with this island best.
Well,
so, you know, where should the bridge feet be, et cetera, et cetera. But,
yeah.
Evan?
But actually the island, the modal system of the island is quite simple. You know, it substantially acts like a rectangular plate. But it's even made in some ways simpler by the fact that the F-hole edges are free, so that they move very, very easily. There's no added stiffness right at the edges. So you can look at where those modes are, where it moves from being one continuous, a whole sort of platform that rocks together, to one where it starts to bend, and then one where it bends, you know, more nodal lines. And these occur at quite discrete frequencies.
Absolutely. This comes up completely in my computations. One actually sees what the vibrational modes of the island area are. and you can see which ones couple strongly to the bridge and those that don't. And
And
it makes,
sometimes an Oberlin will be close to your bridge foot, and sometimes it won't.
Evan?
Sure. So I think about that area between the F holes is going to be your tweeter. Also, we have to pay attention to where the audience is relative to the structure of the instrument. So looking forward on top of the, normal to the bridge versus normal to the back, nice directions, but our audience is kind of tangential to that. So you're kind of looking at the side of the violin, not directly at the top in most times.
Yep.
And to get that directivity, you really want to have a rocking mechanism because that gives you a dipole that's along that level. And it throws most of your energy to the side. So, these kind of rocking modes in the area are important. Jansen's work with cutouts has always intrigued me because that tunes how the system works. That's the in cut of the upper eye of the sound hole and how that traces out. So that shape seems to be important in his work. And of course, the bass bar is dominant in that area too. So if we're going to look for on any instrument, where is the sound ending up? We're kind of shooting it off the side, not necessarily in the lateral side. So if you look at Tool's work in loudspeakers, he sat there and said, well, I'm only really concerned about that front region. So that's where I'm going to take my measurements and analysis. And the rest of the room gets kind of some energy, but I'm not really concerned with it. So, and looking at the violin, which way are you pointing it? Now, you're pointing to an audience, you're pointing to band members, it has a more interesting relationship. But the rocking motion in the Bridge Island area, I think, is critical to its projection into the audience.
Well, that suggests we could try at Oberlin this summer, because we have some nice acoustic spaces, is having a blindfolded audience, and have the player turn around to different, can people tell? We think we can, but yeah, that would be interesting. How important, in a good listening space does it make? I know when I have the impression in halls when violinists, the soloists sort of lean forward and do that, you sometimes feel a wash of highs going over you. So I expect there's some truth in that.
I think that needs to be a blindfolded test.
Yes, exactly, exactly.
And I also think that the power response of the instrument depends on the directivity, even if you're in the reverberant area where you can't tell directionality. So,
I see. Yeah.
So if you had your tweeter pointed to the ceiling, it's pointing out tremendous high frequency energy, but it never makes it past the first reflection.
Mm-hmm.
So there's a bunch of room acoustics that muddies the water here a little bit.
And it's certainly true that the upper hill, the 4 to 6 region, it really does, I mean, from my measurements, comes straight out the front. So it's really heading for the upper mezzanine or
right.
something like that.
It's physically doing that. Is that useful is the next question.
Well, who is the David Fan? Who is the guy who came to, who does the sound reinforcement system?
David Griesinger.
Yeah, he emphasizes the importance of direct highs to the clarity, perceived clarity of lines, so and that impressed me. If it's true, is that controversial? I have no idea.
I think it's uncontroversial in the sense of that specific context, but it is slightly controversial in concert hall acoustics design because there's disagreements as to what constitutes a good concert hall.
Oh, that's a can of worms we'll take longer
yeah,
than
exactly, because whether you emphasize clarity over other factors. So
right.
Enough said about that topic.
Okay, Marty, take us away in a different direction.
Question for Luca: when you glued the bridge on, did it change much?
Did it change much about the instrument if it's not glued on or if it's glued on? I don't think so. I haven't looked at that measurement, but from my recollection, it didn't immediately look very different or something.
Well, makers quite often stress having a good fitting feet on their bridge. And I was wondering if that had an effect, the gluing.
I don't, in the measurements, I don't think, like I've had some not that well fitting bridges on instrument and then fit them much better. And I have never observed a big difference in the measurement. I don't think that tells us that it doesn't make a difference, but I don't think the measurement is really very sensitive to the fitment of the bridge.
And there's obviously some limits there. I mean, if it's a professionally fitted bridge, I don't think it matters how perfect it is, but there's some bridges where you say, okay, that's really not doing its job.
Yeah.
Well, unrelated to that, we did, Luca, didn't we do a set of measurements without the neck?
Yeah, so some of
the
measurements I showed were without the neck.
And it was similar trends, right?
Yeah, that didn't really change much if the neck was on there or not. If there's no strings on it, of course. I mean,
right. So it does say again, we can, before you even set the neck, once you have the closed body, you could start making some, important or useful measurements about, where your instrument's heading.
Are you doing that already, George? Because you did this?
Yes. Well, I mean, I think you can surmise a great deal about the finished instrument once you close the box. So and it gives me, if I want to open it, that's a very good time to do it. Because
right.
I will still not have trimmed the edges, and it's not varnished. I can get the top off, even if I have to slop lots of hot water around. Actually, I never do that. I never use hot water. But I mean, yes. I mean, there are certain key frequencies, and I think the transverse dipole is one of them. Another is the B1 plus anticlastic bending frequency, and CBR. So B1 minus and A0 are
Oh, I think George, we just lost George's connection.
Yeah, I think he crashed.
All right. Joseph, Marty, are you done?
now.
Okay, we have George back.
Yeah. I say, what was I talking about?
B1 minus and A0 on just the corpus.
I don't think A0 and B1 minus are particular, apart from their amplitudes. I don't think their frequencies are an indicator of very much finished instrument. But I think there are two crucial corpus bending modes, and that's CBR and the B1 minus corpus bending, which is pure anticlastic bending. Then what were the other two I said was the transverse dipole. And you could look at one or two others higher up, but I think if you just looked at those, you've already got a pretty good idea of what that violin is going to be like.
Do you put a Soundpost already in your corpus then for the measurement?
Without a Soundpost.
You do it without a Soundpost?
Yes.
And then you can kind of assume the Soundpost will probably do something like this.
Assume that it's the same. It's basically the box of the same quality and properties, but perturbed by the added Soundpost.
Yeah,
absolutely.
Has anyone tried taking a top and putting it on a bunch of different instruments? If they're all the same model, I'd be quite interested in doing that. How portable is the character of the instrument with the top?
Yeah.
Marty, is your hand still up, or that's just, you haven't turned it off? Could you turn it off then?
Just on Joseph's last question, someone who can remember the Bilbao experiment, did they in fact have instruments with essentially the same top on different bodies as part of that data set?
That was the intention.
Yes.
So there were 4 tops that were supposed to be identical, and 4 backs that were supposed to be identical.
And did they migrate top from one to the next?
No, we didn't move them.
Oh, okay.
But part of the idea is that the instruments were going to be preserved as, a finished item that people could play with later. I mean, I suppose it's a possibility that somebody might say, enough time's gone by, let's swap the tops around and see what happens. Because really what the back and ribs do is they provide the boundary conditions for the top. So in fact, you would expect there to be some difference if you move the top for one, particularly a very different set of ribs and back. You'd expect, obviously you would expect a big difference. But if they're similar, not so much. But then there are qualitative differences that musicians perceive that are not at all the ones that we as researchers were looking for in the experiment. So as researchers, we were looking for the people's ability to pick out the kind of Z values of the plates, which those of us who had attuned ourselves to it were able to do consistently. But other people, musicians who hadn't had any induction into that thinking, they were looking at entirely different features that are quite meaningless to us, but very obviously meaningful to them. But there you go. There's your problem with psychoacoustics.
Mhm.
Well, they're two different jobs, aren't they? And they both need to be done.
Yeah. So,
Indeed.
Joseph, you made a remark. I want to make sure I understood it. You said in your presentation that there was certain of the measurements for different scenarios. I forgot what the exact scenarios were, where the differences in the measurements were not as large as you expected. Did I understand you correctly?
I don't remember saying that, but that doesn't mean. Can you give me more clues?
No, I mean, you were looking at the the radiation plots but I forgot which exact slide it was, but it's fairly early on in the slides, and you said that the difference is your remark was something along the lines that, oh, the potential for change wasn't as large as you expected for out of these instruments.
I'm sure I meant it, and I'm sure it was true, but I just
okay, because I wanted to because my remark on that was that when I looked at the plots, because we know from psychoacoustics that over very narrow bands, it's often very difficult to discern differences of many dBs difference in the response if it's concentrated in a narrow band, because you basically don't hear them unless you happen to excite. There's some frequency component exactly in the band. But on the other hand, very small differences of fractions of dBs can be discerned over large frequency ranges. And so when I looked at your graphs, yeah, even though between some extreme differences, the differences might have been only 2 or 3 dBs. On the other hand, they were basically broad. The differences occurred over very broad bands and often could tilt the frequency response. So actually, my conclusion from that particular slide was there's actually a lot of potential there, because if you just even a small amount of response differences over a large frequency band tilting it one way or the other, I think can be discerned by
so you're probably talking about the different bridges on the same instrument, because that's what'll well, a few things to be said. Doing the averages like that, you don't see that there are actually a lot of individual peaks, some of them quite high, that are smoothed out. So I take a third of a dB band average distance shift seriously, even though it's at the lower end of what people could notice, because it means in practice there's often maybe a 6 dB shift in some peaks. But it does raise a background question for me about psychoacoustics. Let's say you created, it's probably best to do it synthetically, an instrument with, let's say in the Bridge Hill region, you had rather even peaks versus one with a few very high peaks, but the same levels. In my experience with instruments some of what I consider my most successful instruments, they have these very high peaks, and it's a very distinctive sound and feel, quite different from, a more level. So I'm surprised you say it's harder to tell, but of course, these aren't very
Okay, so yeah,
narrow.
but there's
They're
more nuances here because number one, that remark is basically from the hi-fi circles where yeah, if you have very narrow sharp resonances, often, like I said, it cannot be detected unless you have a frequency component exciting that particular frequency. While very trained listeners can easily detect fractions of a dB, and for example, an overall level. They may not know, which is actually louder, but that's why, for hi-fi blind testing, the levels have to be matched because statistically, the slightly louder, feedback, the playback will always be preferred. Everything else being equal, even fractions of a dB.
That's why we want to make loud violins.
Well, exactly. But I think the violin has certainly, all of those things are applicable, but there's more complexity to the violin. Because for one thing, as a player, you're playing all sorts of notes, and then so even if most of the notes are not affected by a particular resonance, once you hit those notes that affect the resonance, you can be really bothered by it. Okay. Number one, and then sort of a corollary to that, talking about the way players evaluate violins. There are some players automatically could be the world's greatest violins, but the minute they hit that wolf note high up the G strings, and if they can't tolerate a wolf note, they refuse to anything more to do with that violin. So, it's a more complex evaluation process for a violin.
Indeed.
But I see other people have their hands up. So Colin, you're muted.
Can you hear me now?
Yep.
Okay, fine. Yeah, the other thing is, I mean, it's related to what you've just been saying. Is whenever you're using vibrato, you're going over really an extremely large frequency range. If you're only doing a quarter tone or something like that, which is that's a pretty wide vibrato. But when you get up to high frequencies, you're really ranging over a whole lot of things. And you do excite those resonances, and it means that all the resonances are really become really important wherever they are.
Yeah.
In particular, in the lower frequency range, where you've got very strong resonances, for example, playing near the open D, where you're quite close to the A naught resonance. A player will go back to playing a note there and just saying, look, just listen to this wonderful sound. And it's basically a wonderful sound because it's varying. And it's the variability of the sound, which I believe is one of the most important characteristics that define the sound of a violin.
I totally agree with you, Colin.
I think we should be paying a little bit more attention into looking at that sort of thing rather than overall frequency responses.
Yes, indeed, it's a project in itself, isn't it? It's and it's a psychoacoustic one. I would actually I would like to see a study with using impulse responses and convolution, where we can change a lot of things in the impulse response and really try and get at the heart at, I imagine having like 6 different IRs, and in with the headphones, each player normalizes them for loudness before they do anything else. And then you'd start learning about what is equivalent loudness for people. And then when you have this set, then start saying, what do people prefer and different ranges? But yeah, there seems to me there's a vast amount that can be learned with the methodology that's now, very simple now. But life is short and acoustics is long. Yeah.
Evan?
Helps if I unmute. So Joe kind of touched on it, but when we're doing preferred spectrum stuff on broadband noise, which is a lot simpler problem, is you do have to equalize for equal subjective loudness. Mere mechanical levels don't cut it because loudness is such a complicated phenomenon. And then we get into Colin's thing where you have a time varying signal, it even gets more obnoxious. That the time varying signal gives you a time varying loudness, which is a very complex function. The other thing that kind of going back to something that was touched on about, kind of audio in work done on concert halls, one of the things that makes concert halls more interesting is if there's a different signal coming through your right hand and your left hand ear. That if you've got a uniform sound from it, it's kind of a dead hall, but having a stronger signal coming to one ear or the next gives you more excitement. It's a measure that they look at in concert halls. And if you take a look at the violin, because it's kind of like blasting one of your ears relative to the other one, as far as being entertaining and capturing your mind's activity, is the violin may be set up to be uniquely important in its asymmetric response to the player. The audience is further away from that and is not hearing that difference other than through the acoustics of the hall. So there may be something about the playing of live musical instruments that gives us locally a little bit different sound in both ears, which adds to the interest and the character that we're evaluating.
I'm trying to imagine what sort of a hall would give you a different sound in one ear than the other. Is it?
Imagine something simple. You're just sitting closer to one wall than the other. You're not in the center of the hall.
Okay.
You're gonna get a bounce that's stronger on this ear than that ear.
So sit near the edges. That's a good tip.
Well, the funny thing is,
expensive seats are right in the middle.
Right. Well, part of the study was done early on with a hall that was in New York City that just got panned. It's awful. And yet, because they were using the local college to be all the ushers, everybody agreed there was one really great seat in that hall. And they all agreed on it. And it had some of these properties. So the work was done by the team that came in to rescue that hall. And in the end, they rebuilt it. But a Japanese professor really got into this and actually thought about, in one of his later papers, of being able to characterize every seat in the hall with these mechanical parameters of early reflections and right-left imbalance, so that if you knew what your profile was, you'd know what seat you wanted to purchase.
Fascinating.
Yeah.
So maybe you can tell me, let's say you have your 12 mic positions and you're capturing some directivity. Is there any way of playing them into a virtual space? So into a model of a hall, like a Carnegie Hall. I mean, people are always adding that. Can you put directional that into that and see how it sounds, or is that impossible?
No, it's computationally expensive, but it's doable. Typically, what you'd need to do around the violin would be a spherical array, so you have all the directions, if you will. And then you can basically take that as the source model and propagate it. So that's technically doable. It's done to a certain degree in evaluating halls.
Oh, I see. Okay.
Yeah. It's also used in movies on a little bit simpler manner to give you the sensation of being the audience of walking through the physical space. So you can play some games with that to give you more feeling of the presence of being in the room you're seeing, not the room you're sitting in.
Okay. Shall we wind down?
Yeah. Do we have any more questions or discussions on the presentation today? If not, let's give Joseph and Luca a great round of applause. And I'm looking forward to future developments and findings in this area.